Good morning. I once again welcome the participants on behalf of our workshop team and IBM. I also want to thank the participants for patiently listening the past 2 days, the whole events. And I know the technical depth of each and every program were very high. And I just want to make sure that the participants can actively interact with the speakers and get much out of it. And I will just give a brief summary about how we traveled so far in this particular 3-day event. And so we are in the day 3 now. So we will see what are the things we have seen. And in today's session, what we are going to see also, I will just give a summary. So first, in day 1, we had a session from Open Power course and accelerators given by Dr. Peter Offsey. And then it is followed by the session of Power ISA by Vinod Busa, and he's from IBM. And then we had a session on microwatt given by Satyadan. And then we had a session on system on chip and components from Abhishek Sharma. And then we had a session from System Erilog that is given by Dr. Shashidhara. Okay, and these are the sessions that we have seen in the first day of this particular program. And in yesterday's program, we started with the presentation from SOC design using Open Power course from chiplet integration that is given by Mr. Farhan. He's CEO of Broadback USA. And the second presentation was from Dr. R.G. Das, and he presented Open Power and Advanced System Hardware Features, and he is from University of Alaska. And we had a third presentation, and it is on NMigen, and it is a Python-based hardware design language to design and verify digital circuits. It is given by Satya Dhyan. And finally, we had fourth and fifth presentation from Libre SOC, and it is given by Luke, and is a technical director. And finally, we have the fifth presentation from Varun Gopal. It is on FPGA implementation using microwatt. So this is about these 2 days sessions. For the past 2 days, we had these very high technical knowledge transfer to the participants. And in today's session, we are going to be seeing some of the exciting technical ones. So first, it is going to be given from Google, from Tim Ansell. Okay, he is going to talk about design and open source SOC with Google Skywater PDK. So it is going to be manufactured for free. Okay, Open Power Microwatt FPGA soft CPU core got announced in 2019, and it is a VHDL based design for an open source Power ISA processor core. The microwatt is a basic 64-bit power core that can be run for software simulations or an FPGA hardware. The VHDL 2008 soft core of microwatt remains available via GitHub, while now it is actually fabbed thanks to the eFabless Open MPW Shuttle program. This Open MPW Shuttle program, sponsored by Google, it provides an opportunity for fabrication of fully open source projects using the Skywater open source PDK, process development kit, process design kit. So this program is to provide those with fully open source designs the ability to see fabrication without bearing the cost. The cost of the fabrication, packaging, and evaluation boards are covered by Google. It's an interesting one. And the second presentation is going to be presented by Mr. Arjun Nag from Tata Consulting Services, where he will be covering verification concepts. The third presentation is going to be presented by Dr. Shashidhara from NIE, and he will be covering components of verification and examples. And the fourth presentation is going to be given by Mr. Manigandan Nagarajan, and he will be covering C2S. So it is yes, India's Chip to Startup program. and opportunities develop solutions using open power cores. So we will just see what is the India's chip to startup program. So Indian government initiated a program to usher in a new era in electronics manufacturing by providing a globally competitive incentive package to companies in semiconductors and display manufacturing as well as design. The program aims to train 85,000 high quality and qualified engineers in the area of VLSI and embedded system design. With the help of this training, the government intends to usher the development of 175 ASICs working prototypes of 20 system on chips and IP core repository over a period of 5 years. And this is the significance of it. And we have the final presentation to be delivered. It is on the programming Coriolis to flow for GDS2. It is going to be delivered by Mr. Abhishek Sharma from Object Automation India. He will be walking through the complete flow from zero to ASIC to create GDS2 and providing access to University of Oregon Silicon Systems to all the participants. And the participants can do the experiment and everyone will get a physical chip layout using GDS2 data. Overall, the third day program will have all kinds of technical and practical feast. With all these technical skills, VAT will try to fabricate a special purpose chip using open power microwatt core. Okay, so this is about the sessions that is going to be handled today.
Thank you, Mr. Hariharan,
yes,
for the wonderful summary. I really appreciate it. And with this, without spending more time, I'd like to invite Tim Ansell from Google to start his presentation. Before starting his presentation, I just want to announce his profile once to you all. It's a great opportunity to be with Tim Ansell in this program, and certainly his research interests include open source EDA tooling, open source RTL design, and software speed hardware accelerated development. And Ansell received the BA degree in philosophy and cognitive science and BE engineering degree in information technology and telecommunication. And his interest in open source is it has been proving a lot of things in the last several years. With this, once again, I'm inviting Tim Ansell to start his presentation. Please go ahead, Ansell.
Hi. So just for everyone's information, a copy of the slides can be found at this link. It's in the top right-hand corner of every slide if you forget. And if you see something that you think is relevant or you have something else you'd like to share with me, my email address is tansell@google.com. So just a little bit about me to kind of put this presentation in context is I self-identify as a software engineer. I'm not a hardware engineer, I'm a software engineer, and I've been at Google for about 14 years now. And I've been doing open source since 1994. So I've been doing open source for quite a long time. It keeps getting longer as well. And at Google, I'm in a group that focuses on engineering productivity. And we work closely with all the other groups inside Google, including groups like Google Cloud, Google Research, Google Platforms, and Google Security to try and make it easier for us to deliver the type of products that Google is expected to deliver. And one of the things that I've understood from being at Google for 14 years is that Google runs on computers. And we pioneered a lot of this idea of using large sums of unreliable hardware to really revolutionize how you do application delivery. And we use a huge amount of hardware. And the reason we have a lot of this hardware is because if you look at demand at Google, the demand for all our services is pretty much growing at exponential rates. These are all logarithmic scales on these demand curves, which means a straight line is a logarithmic line. And for most of my career, there's this been great thing called Moore's Law that has meant that we've got a free speed up that keeps up with this increasing demand. But if you look at this diagram, you kind of notice that things aren't going so well these days. There's this kind of been this tapering off, but there hasn't been a tapering off in demand. So what we are looking at is that really we're going to need an alternative way to keep up with this increasing demand. And so we're looking at things like hardware accelerators. And if you've ever looked at hardware accelerators, you can see that moving something from like a software script to hardware can give you quite a massive speed up. And so we think potentially in the future, every project we're doing is going to need some type of custom hardware accelerator to do it. But a problem with hardware accelerators is they're unique to each workload. It's not like a CPU where it's a general purpose thing. It's generally specific to a single function. And for some of our biggest workloads, we've already started building these hardware accelerators using pretty traditional methods. And the question, though, is what about the other people who maybe aren't as big? What about hardware accelerators for them? How do we get hardware accelerators for everyone to keep up with Moore's Law is a problem my team is trying to tackle. And as I said, we've been successful in building hardware accelerators for some applications. These are the TPUs, and they are used for accelerating machine learning, and they've been very successful in accelerating machine learning. But in doing the development for these, we have discovered some things that people have been doing hardware for much longer time than we have known for a long time. And that's one, as these chips have gotten bigger and more advanced, there's been an exponential rise in the cost to create the chips. And a lot of that is an increasing verification cost. And as well, there's an increasing gap between what we would see should be the theoretical performance of a process technology and what people are actually able to achieve on that process technology. And so that's concerning. And what we are kind of thinking about is to resolve these problems, we have to think about the loop that we care about, which is we're really trying to deliver an application. So we have an application, we build a hardware description, then we do some simulation and testing implementation. But by the time you've done this, the application has changed. And so you're going to have to continually do this loop. And we really want to speed up the time it takes to go around that loop. And this diagram kind of hides a huge amount of hidden complexity, right? If I expand it, you start to see how many things are involved here. Just in hardware description, there are many different languages needed. And we've discovered in going around this loop very quickly in software world that open tooling is really an important part of enabling us to drive forward these tooling at a much faster rate and to speed up that loop. And so Google is investing in open tooling in places where we think it's important to our business. And some prime examples of this are TensorFlow. When we released TensorFlow, people thought we were a bit crazy because it seemed like we were releasing the golden goose of machine learning from Google. But we released it because we believe it's going to enable us to get stuff done faster. And we released Kubernetes, which is some of the way we scale, data centers. So my team is trying to apply this to changing how we do hardware development. And we believe that this open tooling investment is really going to enable new innovation, it's going to enable new experiments, and it's going to enable us to deliver new products. And so the strategy that my team is working on has a couple of primary prongs. The first one is that Google internally is a very big system Verilog shop. So a system Verilog is one of these hardware description languages. You may have heard about VHDL, that's another common one, but Google mainly codes in system Verilog. And so a team who's led by Hannah Zeller on my under me is trying to improve the state of system Verilog and make it a first-class language in these open source tools. And I like to say that, you know, system Verilog is to Verilog like C++ is to C. The interesting thing here is that these hardware description front ends needed to pass system Verilog benefits both ASIC and FPGA tooling. As well, the simulation and testing tooling that is used, even if you're doing FPGAs or ASICs, is common no matter the back-end technology that you're using. And so our work here to improve system Verilog tooling, which again is led by Hannah, is really helping both areas. And to do system Verilog tooling improvements, we have a two-pronged strategy because there are two types of things you need to do. We have variable, which we're using very strongly for developer tooling. And you can think of, if you're from a software background, that this is things like code formatters, indexes, code searching, linting. And because you need to be able to pass your entire code base quickly all the time, we want a very fast processor, and we want to be able to handle unprocessed code. And that's what variable is designed to do. But we also want a library that can actually be used in implementation, and that's what Surelog is. It's basically a front end that can be connected to either a synthesis tool like Yosis or a simulation tool like Verilator. And so this Surelog front end through the UHDM description is able to provide system Verilog support in a lot of common tools that you can use. And this really brings us up to an industry standard level of support for a language that is very important to Google. And so coming back to these prongs though, once you've got the thing into your front-end tools, you still want to do an implementation. And there are kind of two options for implementation. You could implement it in an FPGA, or you could implement it in an ASIC. In the FPGA world, the FPGA tooling is led by Carol. Carol actually works at Antmicro. We partner very, very heavily with Antmicro in the FPGA tooling space. And we want a complete RTL to bitstream tools that are fully open source. And so just recently, we launched a thing called the F4PGA, which is the fully FOSS FPGA flow under the CHIPS Alliance. And this was because we previously had a community run group called Simberflow. But what we've seen is there's been, from this community tooling and having people like Google come in now, we have a critical mass where we really are seeing people start to use these tools commercially. And so the F4PGA was set up under a formal work group under the CHIPS Alliance, which is a formal Linux Foundation organization. and it brings together a full tool chain for doing FPGA development. It's vendor neutral. It targets multiple vendors' FPGAs. It's fully open source. And a key part of it is we're developing interchange formats that allow a lot of these disparate tools to talk to each other. And like a lot of other tool chains, really it's built out of multiple different parts. In the front end, you've got tools like Yosis. And then in the back end, you've got tools like NextPNR and Verilog to routing. And then you've got the bitstream documentation projects that actually allow us to target FPGAs like Project iStorm, X-Ray, Trellis. And when we kind of started this, FPGA vendors were very reluctant to provide us with the information needed to develop these tools. But we've actually seen that has actually started changing now. A bit, I forget when this was now, but QuickLogic became the first vendor to officially support open source tools for their FPGAs. Unlike most of the other FPGAs that are supported in open source tools, these tools are supported by the vendor and the description was provided by the vendor. So the other thing though is, you know, QuickLogic's only a small group, but the big change is that even companies like Xilinx are starting to get on board with this. Xilinx did things like release their Unisim library under Apache 2 license. They're one of the big collaborators on this FPGA interchange format, and they joined the CHIPS Alliance for pretty much the sole reason to become part of this F4PGA working group that now is focused on these open source tools. And so what can these open source tools do at the moment? Well, they support 3 main families of FPGA vendors, but there are more coming all the time. In the Xilinx world, the 7 series and UltraScale and UltraScale Plus are the things that have been targeted. The 7 series support is starting to get pretty good on certain parts. And the UltraScale stuff is still, you know, pretty new, but it's getting there. By far, the best supported parts are from Lattice and QuickLogic, which are a little bit smaller. And these are actually in places where the tool is now better than the previous tools that were proprietary. And definitely for small designs like what I would call a microcontroller size project, the open source tools are really good and can get you really good results. Embedded style Linux projects, you know, single core, 2-core, smaller Raspberry Pi type style projects, the FPGA tooling is getting to a pretty reasonable state as well. Once you start to get bigger than that, the tools aren't there yet, but we're putting effort in to get them to that level. But a set of tools isn't that useful unless you have something to run it on. So we're also investing in things like the ecosystem that is around the tools. We've been investing in the LiteX ecosystem and funding them to develop new cores. Some areas that we've been particularly focused on is the memory controller and how do you attach an FPGA to a computer in a high performance way. And so we're exploring a lot of different options in that space. As well, in the FPGA ecosystem, it's really important that we connect to academics so that we can get new and interesting ideas about how to speed up these tools. because the traditional approach for how to do this is very slow. And I'm a software engineer. I don't like waiting longer than 5 minutes for my things to compile. And many of these tools have compile times of, tens of hours. And so we've been working very heavily with the University of Toronto, who owns the Verilog to Routing project. And their latest release, for example, sped up their runtime by 5.2x, while in the same time reducing the wire length and critical path delay. And they reduced memory usage by 5x at the same time. And so this is pretty outstanding progress here, and I hope to see what they get with the VTR9 release. People at the University of Pennsylvania were able to tune the tools in a different way and take a compile time that used to be 42 minutes and down to 12 minutes using a divide and conquer approach using the proprietary tools. But then they used the open source tools and were able to get it to under 5 minutes. So this is also another example of being able to push things further with the open source tools. Brigham Young University has also been an excellent collaborator. They've released their whole computing bootcamp, which has a whole section on FPGAs as open source. And they created a BRAM patching tool and a whole bunch of other stuff that you can go and play with, all available. And as well, you need to have stuff to run on what you put on your FPGA. So we've been looking at things like TensorFlow Lite for microcontrollers. And how do you do this when you don't have any hardware? Well, you need simulation systems. And we've been working with Antmicro on their Renode simulation system. And then you start thinking about, well, there's a lot of different ways to combine these. If you think about just the Zephyr operating system and the open source tools and TensorFlow Lite and the LiteX environment, you start getting diagrams that look like this. And it kind of shows you the multiplicative effect that having all these components be open can really give you. So that's the first prong of the two ways of doing implementation that I was talking about that is led by Carl. There's also the ASIC tooling side, which at the moment is led by Ethan on my team. And so when you think about an ASIC, you really have three main components that you need. And when you're thinking about a fully open source ASIC, well, the HDL design, there's actually quite a long history of fully open source HDL. OpenCores has been around for extremely long time. There was the OpenRISC processor around for a long time. And now we've seen this massive explosion thanks to RISC-V. As well, EDA tools have had a long history of being open source, and there's actually been a resurgence in fully open source tools thanks to the DARPA IDEA program. And so when we were looking at entering this, we saw there were open source HDL and there was open source EDA tools, and then we got to the PDK data. And we couldn't find any open source manufacturable PDK that could do a reasonably complicated design. And why this is important for the PDK data to be open is if you take this example from eFabless, they have a chip called Ravana. It had fully open source RTL. They used fully open source tools, but they used the XFAB 180 nanometer PDK. And this is a closed source PDK. It's not an open source PDK, not one that you can get access to without getting under NDA, but it works with the open source tools. But because it is a NDA'd PDK, it infects the rest of the ASIC, and they weren't able to create and release a fully reproducible open version of the Ravana chip. And so a lack of this open source PDK data means we couldn't have open source ASICs. And this was something that was really concerning for us because, as I said in the FPGA section, having each of these be open really multiplies what can be done and how you can do things. So this missing open source manufacturable process design kit was a key concern. Lucky, one of the great things about working at Google is you can do things about these sometimes. And so we worked with a foundry called Skywater to release their 130 nanometer PDK as fully open source under Apache 2 on GitHub. And when we did that, this is what happened. The line on here that is the PDK release is this one. And so if you look at that line, in pretty much a week, we had as much traction as some of these other ecosystems that has been around for many years. So it really became clear that this lack of PDK data being open was a real blocker to having this open source innovation happen in the ASIC space. And what we've been seeing is that an open PDK really enables not only a fully open source ASIC, but it enables HDL designs and the open source tools to be better as well. So this PDK is obviously pretty cool, but what's in it? So it's a 130 nanometer PDK, and it's a pretty all-inclusive PDK. It includes 1.8 volt internal and a 5 volt I/O. It has 6 layers of metal, which one is a local interconnect metal. It's inductor capable. It has high poly resistors, MIM caps, and Sonus shrunken cells. It supports 10 volt regulated voltage and high voltage extended drain stuff. And since we're doing since we have released it, we've also now added the ReRAM technology as an option that anybody can use on the shuttles. And one of the really cool things is that now that it's fully open source, we can publish the documentation about the PDK in the same way that many open source projects do. So if you ever used a Python project, you might have heard of a thing called Sphinx. Well, we were able to use that to publish the PDK data. And so you can go to that URL and see the PDK now and like go through it. Here's some of the information about the library naming. And here's an example of some of the rules, design rules that you have to qualify to make your design manufacturable. And this is kind of what the stack up looks like. Normally, I wouldn't be able to show you this. And so this PDK has multiple digital standard cells. It has I/O and periphery cells. It has the base primitives and automated DRC checking using fully open source tools. So you can use that and then check whether your result is manufacturable. It has analog RF primitives and build spaces for both SRAM and flash. And we've finally added some pre-built SRAM macros, and ReRAM was just added recently. And hopefully in the near future, we'll even have some advanced high-speed I/O cells available for this. And to show that the PDK is actually really flexible, James Stein at Oklahoma State University created his own custom standard cells, which you can go and use. And he gave a talk about his process in a talk series, and you can go and watch a recording of that there. As well, we actually have SRAM bit cells. This is what the bit cell looks like. And as you can see, an SRAM bit cell is significantly smaller than the DFF, which gets us a lot more density. However, the problem was we didn't have a compiler to turn the SRAM bit cells into an actual usable block of memory. And that's because Skywater didn't have one of those that they could open source. And so we worked with Matt Goodhouse of the Open RAM project to use his fully open source memory compiler to create memory macros for the Skywater process. And he gave a talk here about how that worked. In fact, the Dial-Up Talk series has a whole bunch of talks from different people, including my announcement of the open source PDK at the beginning. And because this is now something that people can openly talk about with each other, there's a thriving Slack community that has over 2,600 members, where people are discussing all types of different things. If you're into analog design, if you want to do a university course, if you're to RISC-V, I'm sure there's a power one there as well. And as it was mentioned in my introduction, we are also funding a no-cost Open MPW shuttle program because, unlike software, making hardware has real costs involved. And so the idea is to make it free as in beer for free as in freedom designs. And so this is open to anyone in the world, whether you're an academic, whether you're a maker, whether you're a hobbyist, whether you're commercial, whether you're a startup, whether you're a nonprofit. But the requirement is that your design has to be open source and has to be open source down to the GDS. And every time we do one of these runs, we're going to do 40 designs at once. And you get about 10 millimeters of 10 millimeters squared of space on your MPW. There's a standardized harness, and you get back packaged chips. And the standardized harness and the packaged IC is all about trying to make it easier and faster for you to get going and debug what's happening when your chip doesn't work. If you look at the harness here, the harness has a teeny little RISC-V microcontroller and a whole bunch of functionality for probing your user area and controlling things like the I/O pins to allow you to set them into the right modes or to switch them between multiple projects. And what we're trying to do here is, by getting you back so many chips at once, as that your prototypes should not be precious. They should be throwawayable. You should be able to share with your parts with other people because you have plenty of them. And we really want people to try many different things. We are okay with people failing and trying again. If you're not failing at least some of the time, then you're not trying enough new interesting things. And because of the success of the Google funded program, eFabless has also launched a commercial program. This is where you pay for your ICs, and it's about $10,000 US, and you get back 100 QFN or 300 WCSP parts, but there's no requirement that you be open source, and you can get support from eFabless when you do this. They also have an option where you can get back 1,000 parts, and each part costs $20 each. And so this is really opening up what you could do here. And so how has the program been going? Because it was started back in 2020. Well, in 2020, we had MPW1, which was 40 designs. And we'd done 5 initial test chips before MPW1. So in 2020, we did 45 designs. In 2021, we had 3 MPW runs. We had MPW2 in June, MPW3 in November, and MPW4 in December. As well, there were 2 Chip Ignite shuttles which had designs on them as well. And so I believe we did over 200 designs in 2021. And so I'd like us to beat that even more in 2022. And if you look at the designs on MPW1, people had less than 30 days to get their designs in. The deadline was 30th of November, and 45 designs were put in, of which 40 managed to pass manufacturable checks. But one of the really cool things is that 60% of the designs were done by people who had never attempted to create an ASIC before. And we were really surprised at the huge variety of what people have been doing on the MPW program. Somebody was working on an amateur satellite radio receiver. We had obviously a lot of open processor cores from a mix of ISAs. There was RISC-V, but as was said earlier, there was a power processor, and I believe there were even some other architectures. We had the obligatory crypto miner that somebody did, but we also had a lot of analog RF and eFPGAs, embedded FPGA designs. And one of the coolest things that has come out of this is a guy called Matt Venn created a way to build an MPW program out of our MPW program. It turns out 10mm squared is actually quite a lot of logic. And so he was mainly concentrating on much smaller designs. And so he built these tools that allow you to embed 16 designs in a single slot. And when you start thinking about that way, because we get back to you over 100 ICs, each person is still getting 5 ICs, and each project is only 610 USD. And so you might be thinking, well, like, is it too late? Well, no, we have more shuttles running in 2022, and there's more chip ignite if you want to pay for it. In fact, MPW5 is open right now, and the deadline for submission to MPW5 is March 21. And our plan is to run at least 4 Open Shuttle runs in 2022. Our plan is also to launch a second fully open source PDK from a second different foundry. And with launching that second open source PDK, we're going to add a second open MPW program similar in style to the Sky 130 program at this second foundry. And so there'll be even more opportunities to do tape outs. We're hoping to be able to do even more things, like add a third foundry or more. And we're looking at adding a second 130 process node and even a more advanced 90nm node. And because of how successful these projects have been, we are seeing people to seriously consider whether or not they should open source their PDK at their foundry. And so that's the stuff we've been working on. But I want to talk a little bit about where this could go in the future. At the moment, we separate FPGA tooling and ASIC tooling into separate branches. The thing is, an ASIC takes, roughly 2 years to go from, designing to having a full production ready deployed implementation, whereas an FPGA is only a couple of hours at most. You can deploy a new update extremely quickly. And people traditionally do a diagram like this, where they have CPUs at one end, and then they have GPUs, and they have FPGAs, and they have ASICs. And their argument is, well, one is slow but really flexible, and the other one is really fast but single function. And I think this is the wrong way to think about it. Pretty much every FPGA I design, I do has some type of CPU component in it, and has some type of functionality that doesn't change, and has some type of functionality that continues to evolve really quickly. And so the way I see it is, in the future, what every IC is going to be is some mixture of a CPU, an FPGA, and some fixed function units. And different combinations of these and different ratios will be important for different applications. Some applications are going to be very, very static. And so being very, very heavily ASIC is, a perfectly reasonable solution. Other solutions are going to need software speed innovation because the world is just moving too fast for it to be multiple years to do this. And an example of this is the software-defined radio field, where they take 5 to 10 years to deploy a new radio ASIC to every masthead in the US. So instead, what they've been deploying is software upgradable solutions. And some solutions are going to be, a mixture of all three. So in the future, the world might look like we have a single hardware toolchain, which is able to change how you implement these in different ways. As well, something that I didn't have time to talk to about today is, all this has been done so that we can deliver new products. And so we have a whole group on our team whose job it is to go out and make sure that these tools are usable for actually building real world stuff. So to reiterate, Google invests in open source tooling in areas that we think are really important to the future of our business. And examples of this are TensorFlow for machine learning, Kubernetes for cloud, and now we're investing in hardware development in the same way. And the great thing about this all being open source is you can come and contribute to it. You can tape out your ICs. You can maybe get FPGA hardware if you contribute. Frequently, people have found that they need FPGA hardware and they're contributing, it turns up. And I do want to say that really pretty much anyone can help. If you think back to MPW1, 60% of the people submitting a design for MPW1 were first-time designers. So it's not an excuse that you have never done an ASIC before. So if you're interested in working with us in this area, I have some tips. So if you want to become a partner here, don't use proprietary tooling or proprietary PDKs. And I want to be clear that if it's academic only, it is proprietary. It's not open source. Frequently people think, oh, I publish something and say it's for academic use only or non-commercial use. Well, that means Google as a commercial company can't touch it. So it's not available to us. And that doesn't fit the open source licensing definition. So make sure it's fully open source and also create a community. What we are trying to do here is build a community that's able to do a lot of interesting things. Obviously, we're going to do a lot of interesting things, but we don't have a monopoly on smart people in the world. And I think India is, well suited here because you have so many people, right? Like you're, I think, the second biggest country in the world these days. And so you should be creating communities that do things in this area and then reach out and see if there are ways to collaborate with other communities. You're currently focused on the open power architecture, but there is also RISC-V, and they're both open power and RISC-V are open source, so you can share things between each other. You should be building bridges between communities, not segregating communities. And so if you want to find out more specifically about the Skywater program, you can join the announce list. And there's also the Slack channel. And as I said, there are over 2,600 members there now. but there could be more. You could be on that. And lastly, as kind of a bonus, as they said, they taped out Microwatt, and here's a picture of the real die that Anton, who did the tape out, managed to capture last night. So that is the end of my talk.
Thank you, Tim, for the wonderful session. It was very informative, and certainly, there are like 87 people as part of this program right now. Definitely, would have got benefited with all the insights, whatever you have provided in last 30-35 minutes. I really appreciate it. There are questions also already people posted. Maybe I will open up one by one. You can answer them. Hold on. Yeah, Arjun, you want to go with that?
Yeah. Tim, thanks a lot for sharing all the resourceful insights. It was very informative. First of all, thanks a lot. So my question here is, Tim, what is the procedure to be followed, right, to set up an MPW shuttle program in India? What are the steps to be followed? Actually, how should we actually go ahead?
Okay, so I've done this once, and well, 1.5 times. I'm currently about halfway through setting up the second one. So the first requirement is you need somewhere to do the manufacturing that is open to having a fully open source PDK released of their process technology. And so that's kind of step one. Step two is you need somebody that is willing to cover the cost of manufacturing. And in many cases, companies like Google could be that. It's certainly something that a government could do, like the Indian government could foot the bill of the MPW program. And lastly, you really want to think globally. The Skywater program, is manufactured at Skywater Technology is in the US, but it's had submissions from around the world, right? There are multiple groups from India who have submitted to the Skywater program. There are groups from, Asia. There are groups from South America. By opening it up to the entire world, it means that people from other parts of the world can end up doing manufacturing in your region, right? Like if your foundry spent a huge amount of money to build that foundry, right? Like foundries are not cheap to build. For Google, one of its most expensive things is, software engineers. But I think Silicon Foundries are probably one of the few things that are more expensive than Silicon Valley software engineers. And so if you've spent all this money building this foundry, you want to have as many customers from around the world as possible. And especially on these older process technologies, which is where my team has been focused most of the time. The open source tools are getting very good for these process technologies. And so that really opens up who can do a chip, right? And I come from Australia, but I've been living in Silicon Valley for 4 or 5 years now. And one of the things we see here is this whole startup culture of trying lots of things, right? You don't know what the next big idea is going to be. You don't know what the next successful, super successful, like hardware design is going to be. Because if you did, you'd already be doing it. Crazy ideas and the next big thing look like each other, because if they didn't, people would be doing it. So really, you want to focus on how do you get as many people through this program. So one of the key things that we looked at is if you're doing an MPW program, normally they're optimized to try and get the cost down, assuming there aren't lots of designs being taped out. We took the other assumption. We went, well, if we are going to do an MPW program, every time we do a run, we're going to do 40 designs at once. And that's what got our cost down to less than $10,000. So, you know, you want more and more designs. As we get more and more of these runs, it gets cheaper and cheaper for us to figure out how to do the masks. So, you know, the mask costs have stopped dropping. And so this is really what you need. You need to increase the numbers. And you've got a really, you know, exciting opportunity here, right? Because you have, again, so many people and you have a very strong education system. You could set up programs where it's not unreasonable to get thousands of designs, you know, a month. And when you start doing thousands of designs every month, the economics around how you do these programs totally changes. And it would, I think, probably drop the cost of doing this by 10x. And so, you know, that's a very exciting thing then, right? Like, imagine if it only cost $1,000 to do a new IC like this, right? So that's my opinion. And, you know, there's lots of other ways to do it. And I do want to see more people trying this. And if you release it as open source, we can, you know, borrow from each other.
Right, right. So Tim, what is the way to propose some solutions actually where Google can fund it?
So our kind of approach here is we want a hands-off approach. We don't want to have to make that decision. So what we're hoping is that as the number of applications come in, we can just keep scaling the number of slots that are available, right? Like, if, as I said, if we are going to make decisions, we are going to bring our own biases around what we think is and isn't going to be successful to the selection process, which means we're going to miss opportunities that otherwise would be, you know, options that are out there. And so that's kind of why we are trying to have a very hands-off approach there. Plus, it turns out evaluating things is very expensive to do. Human time is very expensive. And how do you evaluate a eFPGA against a satellite receiver? Like, they are totally different categories. And, you know, how do you evaluate something that has a 10% chance of working, but is 100x better than something that has a 80% chance of working, but is only 10% better? Like, which option do you do? Well, I don't know, let's just do both.
Mm-hmm. Got it. Thank you. Thanks, Tim.
Thank you, Arjun, for the question. And anyone else have questions for Tim?
So I see two questions in the chat there.
Look, Pradyuma in a Q&A session, she is asking a question about what is the way forward.
Did I lose you there?
Ganeshan, are you there?
I think we lost him. I can see the question in the Q&A. So I guess the disparity between what is taught in college and what is happening, you know, in the outside world, I've seen before. And this was fairly common with software for a long time. And one of the things that really helped the disparity was having fully open source solutions that anybody could download. And once the professionals, hobbyists, and academics are all using the same tools, it becomes much easier for people to transfer knowledge and to figure out the best way to do things. I am pretty sure we're nowhere close to figuring out the best way to do software, and software, development has had a lot more innovation in this space. And things, when I started being a software developer, things like GitHub didn't exist. And revision control systems were only new when I started. So, there's definitely a lot of stuff that we don't yet know. But I do think things like our programs really do help, because it makes it within possibility for undergrad courses to do things like chip tape outs. If you're doing a chip tape out and you're only concentrating on like 7nm nodes, only the most top universities and the top students at those top universities are ever going to get a chip tape out. By focusing on these old nodes, which are significantly cheaper, we can do significantly more tape outs. And while the performance might be less from an absolute, I'm a strong believer that if you attempt something 100 times, you're more likely to get a good result than if you attempt something once. And so I think that's a really big, important aspect here of this. And it's much harder when everything is behind NDAs and you can't find out what's, even the options.
Okay.
How are we going for time?
Yeah, we are okay with the time. Any other questions, team, for Tim?
So I see
3 more questions in the chat box.
Yeah, 3 more questions in the chat box, Tim.
Yep. So there's no current criteria for MPW 5. You have to just produce a result that is manufacturable and pass an automated manufacturable check. And you have to fit within inside the 10mm area. You can use 1mm or 10mm. It doesn't really matter. We don't do any, analysis at the moment. It's just a case of you need to pass manufacturing checks, otherwise we can't manufacture your design. The next question was, is there any way to verify and find bugs in hardware? I'm assuming verify and find bugs in hardware. Yes, there are lots of different ways to do this. And I think we're only in the infancy in figuring out how to do this. The verification costs in hardware are going up so substantially that I think we need to find new approaches for verifying hardware. And I think some of those new approaches is to make it less costly to make a verification problem in hardware. So one of the really important things, I used to be a developer on Chrome, and one of the things we learned with Chrome is that for something like Chrome, we need to basically update it all the time, because it's impossible to make a piece of software that is 100% secure and 100% bug-free. What we have is we need to continually improve it. And so how do we do that with hardware? Well, I think it's going to need more things like embedded FPGAs and other pieces of hardware that can evolve as the needs evolve. And we're going to need more reconfigurability in that area. And so very much, I think there's a lot of research still left to be done here. A lot of people are very interested in formal. There are a lot of people at Google who are very interested in formal, but definitely I don't think that's the right approach. I think we need to take a look at more things like fuzzing and these type of things. So yeah, I'd like it is a complicated topic, and it like is made worse by the fact that human communication is not precise, right? Like, how do you design a piece of hardware to, you know, accurately enforce human laws when even humans struggle to figure out what every law means and how they interact, right? Like, there's a definite problem in there are plenty of bugs in things we want things to do. So, you know, it's a hard problem, and we still need to do a lot of interesting things there. So the next question I've got here is, can AI design chips faster than humans? And my answer to that is kinda. So the AI has a bunch of advantages that humans don't have. It doesn't get tired. It can run all the time, and you can clone lots of them and try lots of them at once. And once you've taught one of them this, every one of them can learn this. And so this is an interesting area for research, and I think it's a very rich vein of research. We don't know yet. For the paper with like the TPU floor planning, a human still had to create the design. It was just that the AI was better at playing the game of arranging the blocks. And, you know, that is something that, you know, a human has a preference about the aesthetic layout of the chip. It's unclear that a aesthetically pleasing chip is necessarily a efficient chip. And so what we discovered with the AI example is that actually, in many cases, a ugly looking chip performs better. And some of the constraints we are putting on it because we're a human and we want things to like fit nicely together in nice groups, were slowing down the chip. And so like, that's really interesting. And again, kind of points out to, we have to be really careful about, you know, our intuition on these problems. Human intuition is set up for a world that doesn't exist anymore. You know, so, and human intuition doesn't necessarily apply to making effectively rocks think, right? Like, I really like that idea. We somehow tricked, you know, rocks into thinking for us. And that's a pretty cool thing.
Yeah, one more question, Ansell. Thank you. Thank you. There is a question from BS Rao. As this is a completely open source, yeah, you can read out that in the chat.
Yep. So as I said, your design needs to be completely open source. So that includes all third-party IP. So this means that we need the open source community to create this third-party IP, and that's why we're focused on open source designs, because it allows us to build this ecosystem. If you use a piece of closed source IP on this design, then nobody else can replicate your design, and so nobody else can benefit from your work. Whereas if you create something that's fully open source, even if it's not particularly good, having something that is not particularly good is generally better than not having the thing in the first place. So definitely we'll want completely open source designs here, because it allows us to build on top of each other. You know, the idea of building on top of giants. You know, Google itself was built on top of, you know, open source software. You know, we use Linux heavily. We depend on, you know, the internet to deliver Google to you. And, you know, we depend on things like GCC and LVM to compile all our code. And, you know, we actively contribute to these projects as well, because, you know, developing all this stuff ourselves would not be sustainable. And so that's a really important thing, is like It's in our best interest as a commercial entity to build these open ecosystems because it makes it easier for us to do things that make us lots of money. So I do want to we're not doing this out of the goodness of our hearts. We're doing this because we think it's a good way to make money.
Very good. That's awesome answer. Sure. So any other questions for Tim? Okay, I think certainly, the last 1 hour, more than an hour, was very productive. And thanks, Tim, for your, wonderful presentation again.